topic 3 of IB Physics, thermal physics. So, looking at the book as my cheat sheet for how to tutor this, state that temperature determines the direction of thermal energy transfer between two objects. So, if you have two objects of a given temperature, I should probably get around to defining temperature. Let's do it how the book says. We have two objects of the same size, and we'll say one is hot and one is cold. So I use red and blue. So this one is going to be red. So I'm going to do this probably a bit. Do you think I should do this weird?
Do I?
Do you?
Do. That's.
You think I should do this weird? That's time to start.
What are you gonna do?
Something weird or something less weird? Of course, weird is a relative term.
Exactly.
Yeah.
I don't care.
Okay. I'll do it.
Up to you.
I'll say that this is red as in it's high in emitting infrared radiation because it's so hot that it's actually I'll say it's even emitting stuff at the low end of the spectrum because light, the more energetic it is, the higher the frequency is. So red is a really low frequency, so it's emitting that. This is hot enough to be emitting a blue. So that's, no, I don't know what temperature that, I don't know how that would be. So I'm just going to say this is 100 degrees Celsius, and this is 20 degrees Celsius. And 20 is too hot. Say, let's say 0 degrees Celsius. For those who are in America, system's weird. This is all based on water. So this is freezing point of water, this is boiling point of water, but the point is that these aren't water. So let's use green because it's the one that I haven't used yet. So here we can tell that because that, let's say these have the same mass, what's going to happen is that the heat is going to transfer from the hot end to the cold end. And then what's going to happen in the end is, basically after this is all done, we're going to end up in an equilibrium state, and if these both have the same mass, then what that should result in is, fill that in there, so go ahead and add some blue here to show that it's cold. And that red, fill the rest of that in. Add some right here to show that it's warm. So after a certain amount of time, these are the same mass, and these are their starting temperatures, and they don't melt or change state, they should end up both being 50 degrees Celsius. So there's the direction of thermal transfer. Kelvin and Celsius scales temperature. Here's that. So why is Kelvin so much better than Celsius? Because Kelvin is an absolute scale. And so Kelvin and Celsius, there are three main types of temperature units. There's Fahrenheit, Celsius, Fahrenheit, Celsius, and Kelvin. Celsius and Kelvin, but like Fahrenheit's weird, so let's get rid of that. Celsius and Kelvin have the same interval of temperature change between them. So a 1 degree Celsius change in temperature is the same as 1 degree Kelvin change in temperature. Or not 1 degree Kelvin, 1 Kelvin. Yes, the other thing is Kelvin is an absolute scale. 0 Kelvin is minus 273 degrees Celsius. And it is absolute 0. And that means that when we say 18 Kelvin, we mean double 9 Kelvin. While in Celsius, 50 Celsius is not double 25 Celsius, so 25 degrees Celsius. So if you want to convert to Kelvin, basically that temperature in Kelvin is the same as that temperature in Celsius plus 273. Moving swiftly onward, state the internal energy of substance at total percent. Okay. So your internal energy is the same as the total kinetic and potential energy of that. Stated. Explain and distinguish between macroscopic concepts of temperature, internal energy, and thermal energy, heat. Not exactly sure. Oh. Define mole and molar mass. Okay, let's talk about the heat. What is actually, before we get to that, we're going to have to talk about the particular model of matter. Basically, the concept began with someone thinking. Let's say you have a bunch of material. You can then cut that material up into small pieces, and then get rid of a lot of those pieces and just keep cutting pieces until you get smaller and smaller and smaller, so that you get this indivisible point that they then called the atom. And then we found atoms, and we found that they're not indivisible, but that is not the point. The point is that at one point you get to the individual particles, the molecules and stuff that we look at as their own entities within the larger entity, or things that make up your thing, rather than just the pieces. Like if you're to break something with a hammer, you have small pieces. Just keep breaking that until you get to the point that a hammer isn't going to be a good tool. And that's probably before molecules, actually. So this is where we're going to get to the mole. And this isn't sponsored, so I'm just going to cover up the label. So the mole. So let's say you have an atom. What atom should we be looking at? Don't say something cesium, unless you're going to pull up a periodic table.
Atom? What could be a good one?
I would say oxygen. Let's say take oxygen, which has is this how you write it?
16A, yeah.
So here, it's big enough to be seen on camera, probably, but you low resolution weird. So oxygen 16.8. This is the nucleon number. This is the proton number, and the nucleon number is the total number of neutrons and protons inside of it, and they basically have 1 unit mass. Not exactly what. U. Whatever unit you use, it's going to be different. But the point is that the electron, that's the other part of the atom, that there will also be 8 of them. It has a negligible mass, so we don't care about it. Its estimation is a big part of physics. So the idea is that I'll write that back. There's some number of oxygen atoms that will give this number in grams. So, and that works for the same for every molecule. That number is 6.022 times 10 to the 23. And that's, if you have this many of any atom, then you're going to have the nucleon number in grams. So this many oxygen atoms with 16 grams. That many carbon what's carbon? That's number 6, right? So that's like 12 grams?
Yep, 12.
Yeah, because also if you remember the periodic table up to like 20, and you don't remember the nucleon numbers, you can just remember that generally, for the starting ones at least, the nucleon number is usually twice the proton number. So we've got that down. 3 states of matter. So we all know about solids, liquids, and gases, I hope. You'll take a solid, say an ice cube. that says, so what's the definition between them? One solid retains its shape, unlike the other two. The liquid retains its volume, while the gas does not do any of those. Whereas solids retain their shape to a point. So, although, let's draw this back up. I keep erasing, I'm having a bad habit of erasing things today. Puddle, paper lines. So what do the molecules look like inside of this? They're going to look like in some kind of grid. What's this? Like sodium will end up in this kind of grid, right? Sometimes. Am I thinking of something else?
What?
I'm thinking of basically what makes this kind of grid.
Solid.
Yeah, but this is too aligned a grid for any solids. Like just some molecules will like crystallize like this. It seems like some kind of crystal. Although I haven't taken chemistry in a while. So what we're going to see is that, like, if we see the movement, it's just going to be these arrows. They just kind of wiggle between each other. You can imagine them attached to springs. They can move around a lot, but they don't break away. And if they do break away, that's a process of melting. So I'm just going to leave that up, but I'm not going to start erasing or drawing more arrows because I think you get the point. Let's get the liquid. All of the pieces kind of like slide against each other, just moving around each other. And yeah, you can imagine it. I don't know, how would you imagine it? Like sand. You pour sand and all the pieces just flow around each other just fine. Now the gas is where it gets different. They spread out a lot more. They just kind of move around and occasionally bounce off each other, but they normally don't like touch or anything. They just kind of move around wildly. I should really define the borders of this area. Which I'll do. Well, talk about. Okay, there are more states of matter than that, but you can actually get to the point that the electron will break free of its atom. But we're not dealing with plasma here. You see? And next part is density, apparently. Or, this is giving a worked example. I'll do the same as the book, following its example. Let's give some worked examples about moles. Let's say you have a kilogram of oxygen, which is a lot. How many atoms do you have in it? I should probably draw that figure. Maybe I shouldn't have, my handwriting sucks. So let's say you have 1 kilogram of oxygen. How many molecules do you have in that? First thing we do is find out how many moles that is. So that's, whoa. Okay, and that is 1,000 grams. And the window just opened, so if there's a really annoying noise, then that's it. So that's 1,000 grams divided by oxygen has 18 grams per mole. I'd say that's about 1,000. Actually, let's say it's 1,000 exactly. Exactly 1,000 grams. So what we then do is plug that into our calculator, and if you don't have one, then figure it out yourself. It's going to be difficult. And let's say that's about 1,000 because I don't want to deal with all these decimals. That's going to be, let's say whatever here is our amount. I have 55.5, let's say it's 56 moles. We're dealing with a whole number of moles because I'm too lazy. MOL for mole like the animal. Uh, Although you could find out how many moles are in a mole, although there are many different atoms there, so it's just irritating. So 56 moles. That is, how many atoms is that? That's 56 times Avogadro's number. 2 times 10 to the 23 equals 56 times 6.02223. 3.37 times 10 to the 25 atoms. So yes, that's a big number. There are a lot of them. So, hopefully that got the idea of moles down. Don't remember moles being in this topic, so that shows how much they're actually useful in this area of physics. Now let's talk about density. Okay, so let's say that 1 kilogram was in an area of, let's say, 1 centimeter cubed. And so then you take your your density is your mass over volume, which is 10 to the minus 2 centimeters cubed. So that would be 1 times, what's that? Yeah. Oh. So that is 100 kilograms per meter cubed. So there's that. Yep, so we know that we had that many molecules, and this is how dense they were. You might be given a density. Basically, what you remember for this is that your density D equals mass m over volume V. Just memorize that, and you should be fine for all these questions. If you're asked for the, there's one that I got that estimate the size of an atom when we give you the density and the mass, and then they give you the density and the mass, and you know the atom that they're talking about. So from there, you figure out how many atoms there are in there, and then you find once you have the number of atoms, you know the mass, you know the density. So then you arrange for, and then you just find volume by dividing the total volume you have by the number of atoms there are in there. And that should give you the number of cubic meters, or centimeters, or whatever unit, parsecs, cubic parsecs of oxygen. That's what we should be dealing with. Internal energy. Let's talk about this. This is something that I found really cool when I first did it. The idea that you could translate kinetic energy directly into heat energy. Let's say you have a car. Also, any questions?
Nope.
Yeah. Here's the question: why do you suck at drawing so much?
No, it's beautiful.
Yeah. Absolutely beautiful. This is the car that I want when I get a car someday. And let's say it's going at a speed. What kind of speed? Give me some non-relativistic speed.
120 kilometers per hour.
Okay. Moving at 120 kilometers per hour. And then it comes to a sudden stop. We're not dealing with acceleration. Doesn't matter how fast it stopped. What it does matter is the fact that when it stops, for some reason, none of the heat went to the ground. It all went into the tires when braking. So so all of the kinetic energy is transferred into heat energy in the tires. Each tire is. Oh, did I talk? Oh, I have to finish this equation. So the equation is. Where can I write it? I'm gonna write it in blue. Q equals mc delta T. Delta T, change in temperature. Delta represents change. C, specific heat capacity. Basically, by definition, it's the amount of energy it takes to heat 1 kilogram of your substance up by 1 degree Celsius, or 1 Kelvin. Mass, number of kilograms.
And what unit is temperature?
Temperature is in Kelvin or Celsius, and the change in Kelvin Celsius is the same, so it doesn't matter which one you use. This is joules, kilograms, joules per kilogram per Kelvin, and Kelvin, or Celsius. So now that we have that down, let's say we have a tire with a specific heat capacity of, let's see what's given here. It doesn't even get the equation. Okay, let's make one up. Let's write on the car. This car is graffitied with the physical information of the car. Tires have a C of 1800 joules per kilogram per Kelvin, and so we have. They also weigh something like 30 kilograms each. So it comes to a quick stop. By what temperature do they rise? Well, let's look at the change in energy. This black shouldn't have been in my labeling system. Change in energy, so it starts with energy, mv squared over 2 equals the total mass of the car. So let's make a big M. Is 1200 kilograms. That is 1200 times. Convert these units to meters per second. So that is going to be 120 times 1000 divided by 60 squared. 60 meters per second. 60 because a minute is a 60th of an hour. A second is a 60th of a minute. Times by 1000 kilograms is made. A kilogram is made up of 1000 grams. And a kilometers is made up of 1000 meters. What am I saying? A kilo is 1000. That stuff. 100 over 3. Fantastic. 33.3 meters per second. So times 33.3 to 1200 times 33.3 divided by 2 is 20,000 to 20,000. 2 times 10 to the 4 joules, or 20 kilojoules, which I'll go with here. So what temperature does that raise the tires by? Well, there are 4 tires, despite the fact that I've only drawn 2. So each one will get a quarter of that, so each one gets 5 kilojoules pumped right into it. And that know M, we know C. What is delta T? So we rearrange for that using algebra. That is delta T equals Q over MC. Equals, and from this, written this way, you can tell, we can see that it's intuitive. If you have a lot of the substance, it takes a lot of energy to heat it up a bit. If the specific heat capacity is really big, it's going to take a lot of energy to heat up. If these are both really small, it's going to be really easy to do. So here we know it's 5 times 10 to the 3 divided by 30 times 1800 equals that is 5,000 divided by 30 times 1800. 5 over 54, 0.0926 Kelvin. And from here we can figure out its final temperature if we know its initial temperature. So whatever temperature it started out with, it's going to have this much more. And there you go. Any questions at this point?
No, that's fine.
Moving onwards. Temperature and particle model. Why not? So we talked about the way that molecules move around differently, depending on the state of matter. So leave solid for now. The kinetic energy of those molecules is what heat is. So your temperature is determined by how fast molecules are moving, and their freedom of movement is dependent on the state of matter. So they're moving a lot like this, and it's a really hot gas. They're moving a lot like this, it's really hot solid. They're moving like this, it's really cold solid. They're moving like that, it's really cold gas. And I left out liquids because liquids are boring. They're being half-assed at being solid or gases. Don't let anyone tell you otherwise. Unless they're... Oh, you can let them. That's fine. We talked about that. Thermal equilibrium. Let's talk about that. So if you put a hot thing in a cold environment, they're going to the hot thing is going to heat up the cold environment until they reach what's called an equilibrium temperature. Now to find what that equilibrium temperature is, we use meth.
Meth?
We can use meth in combination with math, but math is the thing we use directly. But, so let's say we have this really cold box at 0 degrees Celsius. And then we get a really hot box at 10,000 degrees Celsius. But let's make the 10,000 degrees Celsius thing a lot smaller. And this thing, we have how many kilograms?
What thing?
This one.
That 10,000
Yes.
looks small.
Yes.
Let's say 50.
50 kilograms. So basically my mass in this, and then this thing is going to be something like, how much would you say this is? It's a lot more. this whole box though
Yeah,
just
yeah, yeah.
entombs this one. Or we can say this is a liquid and we dropped it in.
50 times 10 to the power of. How big?
I think let's say 4.
What? I was thinking on a
Yeah.
bigger scale.
Yeah, but you know what happened last time I tried to use big numbers? It didn't turn out well. So we can say that this is either a liquid, or we can say it just entombs this inside of like a solid like cement. Except cement is kind of a liquid at first, so let's not say that. Or we can't say that and say it's a liquid and it's still I'm just gonna stop talking now before I say something that I will then have to fix. So, also let's say the specific heat capacity. My lens cap. Specific heat capacity of this object is. It's going to be A, B. This is A, this is B. Substance A, substance B. I would say that's going to be 1,000 joules per kilogram per Kelvin. This is going to be. No, let's put that to the 6 because I'm going to make this fairly low. 50 joules per kilogram per Kelvin. Moving on. Switch to blue because I feel like the blue's being left out. Red and green I don't care so much about. They feel left out all they want. So, moving on from here. So, how do we figure out what the equilibrium temperature is? Well, one thing that we need to keep in mind is that delta T is the final temperature minus the initial temperature. You don't have to use brackets around it because, no PEMDAS, no basic algebra, you'll know that I'm kind of not making sense sometimes. Well, I am making sense, but I'm being unnecessary, which might not make sense to you. Might not make sense to anyone else either. So, how do we figure this out? Also, I should write kilograms there, shouldn't I? So, we know that this one is going to have to lower its temperature, and this one's going to have to increase its temperature. So that means that the thermal energy that this gains is going to be negative. So that's going to be minus QA equals QB. They both have to interchange the same amount of thermal energy. So we know what Q is. So we know that minus MACA T, the final temperature is going to be equal. They're going to be equal to each other. Minus TA, which is the initial temperature of A, equals MBCB T minus TB. And now let's move on from there, but I find that it tends to work better if I don't do it algebraically. It kind of turns messy either way, but might as well start with it messy. So what's MAC? We're going to combine M and C, so that's going to be its mass of 50 kilograms multiplied by C of 1,000, make 50,000, so that's 5 times 10 to the 4 T minus its initial temperature of 10 to the 4 equals, that's going to be a minus then, equals this mass of 50 times 10 to the 6 times 15, which is 2.5 times 10 to the 9. Can I do 9? Can I tell 9 from a 6? Find out next time. T minus 0, which makes this rather simple. In fact, we can simplify this further by dividing both sides by 5, so that's minus 10 to the 4 T. We're also going to expand this. Minus 10 to the 4 times 10 to the 4, 10 to the 8. But also because this is minus, it's going to make that a plus. Equals 5 times 10 that's 0 times that. So, yeah. So now let's group the t's. So that's t of 5 times 10 to the 8 plus 10 to the 4 equals 10 to the 8, and t equals 10 to the 8 over 5 times 10 to the 8 plus 10 to the 4 equals, and hopefully I didn't leave anything out or misdo anything, over 5e8 plus 10 to the 4th is 0.2 not Kelvin, Celsius. Degrees Celsius. And now we can test, we can see what QA is. So I know the final temperature here. So let's do that. MC, which you got earlier, times the final temperature minus the initial temperature of 10 to the 4. And I got minus 5 times 10 to the 8 QB equals, we have we have the mass times the thing. Mass times specific heat capacity times the final temperature, because the initial temperature is 0. And that got 5 times 10 to the 8 and joules. So now that we've checked our answer, we know it is correct. We know that QA is minus QB. This loses the same amount of energy that this has gained, and they both end up at the same temperature at the end. Any questions?
No.
It is. So yeah, you might have noted that that process was somewhat painful. It is not nearly as painful as the process of dealing with latent heat, which we shall get to pretty soon. Specific heat capacity. Change of state, that's actually what we're dealing with now. Change in state. So we'll start with the graph, the temperature graph. Sorry, this. So this is your energy. This is your temperature. So you're going to have some kind of gradient, and that gradient is going to be your, well, per unit mass. So we're going to say per unit mass. This gradient is going to be your specific heat capacity. But then you're going to reach this point, which is going to level off. And then it'll start moving again, and it might even have a different gradient this time. Then it's going to level off again. And then it's going to go again. So what are these leveling points? It's what we call latent heat. At these points, it is changing state. So let's do Q, because all solids are cubic, right? And then, so this is moving from solid to liquid, or if you're cooling it, it'll go from liquid to solid. And then it can go from liquid to gas, or from gas to liquid. And at these points, it's going to level off. And this is because when you get to those points, the bonds are slowly separating. So you have them moving like this, and then eventually they're going to start moving more freely. So during that point, this is not going to gain kinetic energy. The bonds are just going to slowly come apart. So because the kinetic energy can't rise until it's liquid, no, it's just going to stay solid, or it's going to stay at the same temperature as it slowly moves from solid to liquid. And then we have there's the latent heat of fusion and the latent heat of vaporization. And those are labeled. Let's do this. This energy here, that will be your LF. And I just saw the book use L. Yeah, L. So this is vaporization from liquid to gas, from solid to liquid, or vice versa. And this is different for every material, and they should give it to you for the specific materials they're talking about in their book. So, with that in mind, also these temperatures are going to be at this temperature for water. I should probably redraw that real quick. Pick up an eraser. Let's quickly draw that again. Here it's going to be at around at 0 degrees Celsius. When you're freezing it, it's going to, as it forms into ice, and then as you're boiling it here, it's going to, like when you're boiling water, it's not going to heat up any more than it is. It's just going to slowly turn into gas before it can heat up again. So with that in mind, we can move on. Does this book say what the specific heat capacity of water is? Do you remember what this is? Oh, actually I found it. So I can do a question.
1,200. Wait, specific what?
Heat capacity of water, but I found it.
What is it?
It's around 4,200 joules per kilogram per Kelvin. Okay, so let's use an idea that we used in a practical before last year. So we have a beaker of water. That beaker has about, let's say, 1 kilogram of water, and is at a temperature of 100 degrees Celsius. Then you drop in, say, a 50 gram thing of ice at 0 degrees Celsius. Trying to thought, the water's going to be green this time, because green is probably the lucky color, because if it's not, then what is? And this is the surface. So it goes into the water that has a bunch of algae on top that is otherwise invisible. No worries. Water will have a specific capacity of around 4,200 joules per kilogram per Kelvin, and we'll have latent heat of fraction, is that they call it, fusion, is 3.35 times 10 to the 5 joules per kilogram. Joules per kilogram, right? Yes. Per kilogram, not per gram. It's good to know. So, what is, so let's see, what is the equilibrium temperature? So what we did was, we did the opposite. We did this practically, and then we found the latent heat of fusion from the temperature change. So what we know is that this is the amount of energy it takes to melt it, and then it will restart from 0 to heat up as water, which will have this. So it's going to start with mass times latent heat of fusion. This is going to be the Q for the QI, the thermal energy of the ice, plus, so that's Mi, plus Mi, C, delta T, which is going to be final temperature, minus 0. So we can just get rid of that 0 there. T minus 100, 99, 98. Minus here, so we don't forget. And now we shall work this out numerically. Where's my guy? So, this starts with 50 grams. So 50 grams equals 50 times 10 to the minus 3, 0.05 equals 0.05 times like 8th fraction, fusion, 3.35 E5. 1.68 times 10 to the 4 joules plus 0.05 times 4200. 0.05 times 4200 to 10 times final temperature equals, the magnet keeps coming out of this. Very irritating. That's equal to 100 times this times 1, so that's 100 times, that's 4.2 times 10 to the 4. There's the 6. There's the 5. There's the 8. 7. So 5 minus 42. Wait. Yes. 4200 T. Yep. These are switched around because it's a minus sign. And now to work out some more of it. Now we can add these two together and then subtract this from that. So let's get on with that. That's going to be 410 T equals 4.2 E5 minus this equals a very big number. That is 4.03 times 10 to the 1, 2, 3, 4, 5. 5. So final temperature is 4.03 times 10 to the 5 over 4410 equals that divided by 4410 is 91.4 degrees Celsius. Now let's work that out to see if that's true. So Qi is equal to that's 0.05 times 3.35 e to the 5 time or plus 0.05 times 4200 times 91.4. 3.59 times 10 to the 4 QW equals 1 kilogram, 1 times 4200 times the 1 times that times the final temperature of 91.4 minus 100 going to say that the little bit off that it is due to a rounding error I made somewhere during the calculation, which is most likely the case. So you can see that that is not the, well, it's a fairly simple thing to do. It just takes a while and is a bit painful. Oh, look, graphical representation. I'm pretty sure I just showed that. Are these graphs over time? Yes, they are. But I showed them over energy. Okay. Yeah, let's show them over time. Let's say I get a balloon full of hot air, but not a hot air. Well, maybe. Let's say I pull in a hot. No hot air balloons aren't. I mean, like a sealed balloon, full of hot air, perfectly insulated, and I bring it into a cold room. Then I pop it, and this is the temperature of the room. This is the time. This is the temperature. It's gonna look good, and it's gonna start here. Let's say we're up here, and then once I pop the balloon, it's gonna heat up. And then we talked about equilibrium temperature. It's going to heat up and smoothly go into its equilibrium temperature. And I'm not sure if you could ever really say that it truly reaches equilibrium temperature unless you wait for an eternity. But it about reaches there. How is this? Ooh, are we getting to an ideal gas now? Hooray! Kinetic model of an ideal gas. What's an ideal gas? An ideal gas is one that follows the equation. Is it P or is it rho?
I think it's P per.
I think it's rho because isn't it? Or is it pressure?
Isn't it?
Yeah, I think it's pressure. So I guess it's probably P. P. Oh. Screwed up my P.
Proportional.
P. V equals N. Capital R?
Yep.
R. T. Now what's that capital R called? It's the gas constant. That's kind of boring. But here's what it means. It means pressure times volume equals the number of moles times the gas constant times your temperature. And basically, let's say we have 1 mole, and we're which one of these do you want to look at?
Let's go temperature.
Okay, so if we're looking at temperature, we're going to say that, well, let's just erase this and rewrite it. So we're going to say that the temperature is proportional, fancy symbols that I misdrew, but oh well. I'm give it a second shot, but if I fail this time, I'm just going to leave it that way. Proportional to PV. So, that means that at a constant pressure, if I was to increase or, that is weird. So if, let's say at a constant volume, if I was to turn up the pressure, this part would get bigger, and therefore this part would get bigger. And where these are only proportional, you need the N and R's to figure out exactly. And then if you decrease the volume, but keep the same pressure, so you start decreasing the volume, then that means your temperature is going to go down. But usually when you decrease your volume, we can, let's look at volume now. Also, so its temperature is linearly proportional to its pressure and volume. So volume is proportional to T over P. So constant temperature, you really increase the pressure though, then that means that your volume is going to be decreased. dividing by this. So you just press down on it, and the volume decreases as the pressure increases, basically. Or you can really increase the temperature, and then the volume will increase at a constant pressure, because when you heat something up, it's going to expand. But if you, or else, if it won't expand, but you're heating it up, that means that you fix the volume. That means that your P is proportional to your T over V. So as you really increase the temperature, but keeps the volume the same, the pressure will increase. Basically, in any of these, you're going to be looking at the idea of the way that your pressure and volume and temperature are related. Though the ideal gas is not really true, and here's an example why. Here, PV. That means that if we increase our temperature to 0, then we're going to be dealing. If we decrease this to 0, our volume is also going to be 0. So, yeah, that doesn't happen usually, or ever. You can't just gases will liquefy. They won't go down to a single point. See, I often say, imagine how terrifying the universe would be if it followed IV physics. Temperatures would, gases would constantly shrink down to minuscule sizes, and even to absolute 0 probably. Actually, I think they say white. You can't do that. They say that. I think I might have to go back a bit. Basically, the higher the temperature change between any two things is, the faster there's going to be heat moving from one to another. You see in the graph where it starts reasonably fast, and it kind of plateaus. If you're at 0, then there's going to be so much effort by the universe to fill that. As you give that a higher temperature. So at least you wouldn't have absolute zeros in gases, for the most part. Kinetic model, pressure equals. We've talked about pressure. Oh, we haven't talked about this kind of pressure. So let's go more on what the ideal gas is. The ideal gas, the molecules do not tend to interact with each other, and they can be thought of as points. So you put them in a box. You have these dots, and let's say that the tail of the dot, like this one's heading that way because it has a tail, and the only interactions they have that are meaningful are against the walls they contain. Example, that you're dealing with the pressure that's equal to force divided by area. So yeah, when you're talking about the pressure, you're talking about how much force it's exerting per unit area on the outside of the box. That's moving molecules in hot gas. Yep, we've talked about that. How these faster ones are hotter. And when you're talking about temperature, you're talking about the average kinetic energy. Oh, forgot to hide the label. So when you're talking about, here is actually rather cool, even though some of them are moving really fast. The average kinetic energy of the whole thing is really the temperature. Gas does work. So we'll talk about that in a bit. What was that? There's a sound. What do you guess? So where do we get to talk about that? PV equals nRT. Let's do this. We have a pressure volume diagram. Oh. So, pressure and volume diagram. This is volume. So I'm playing the harmonica. I think so. So we can close that window. P. are various types of expansions that will have various different type reactions, and the work is, as we said, force times distance. So when we talk about this, what we're talking about is basically integral of the force pressure per unit area times distance volume change. So we're going to be talking about this area, like an integral kind of thing. And when you see this, they tend to have you do averages. We can do an example. Let's say this happens. You have this state here, and this state here. What would you say the pressure here is? How many newtons per meter squared? This is a simple one. It could be ridiculously large.
20.
20 newtons per meter squared. And this will start at a volume of
10.
10 meters cubed, and ends at a volume of
20.
20 meters cubed. So when they ask you about the work, it's going to be there. Well, first let's think about what this means, so we can get a feel for it, and we'll do that in blue. So PV equals nRT. And here pressure is constant. So what we're looking at is change in volume. Right. Really at a constant pressure. What's your range for here? That'd be pressure, right? It's constant. We'd be looking at a state where P equals nRT over V. And this is constant. That means that if you change T to make it bigger, you also have to change V to make that bigger as well. So that means that this is getting warmer and it's getting bigger at the same time, so that the heat and the temperature cancel each other out. So now let's look at the work that's done. That's going to be 20 times 20 minus 10.
And have you talked about the names of like constant pressure, constant volume, constant?
Getting to that. So this is what we'll call, this is called an isobaric reaction. There's an isobaric, means that the pressure doesn't change. Iso meaning the same. And it also means isolate pressure. You can maybe a barometer is measure of pressure. So you get isobaric, isothermic, adiabatic, and another one that's the constant pressure.
Constant pressure?
Yeah.
That was the constant pressure.
I mean constant volume.
Volume is choric. Isochoric?
Yeah, isochoric. So let's talk about adiabatic, because that's definitely the most confusing of them. So you're going to talk about, it's called a PV diagram. So you have it's isotherms, right? Isotherm lines? Isotherm.
Yes, yes.
So let's look at the equation for an isotherm. So if PV equals nRT, then T equals PV over nR. Right. So that means that when you increase V, when you're increasing V, that means you have to decrease P. And what you end up with case of my excellent artistic skills. And yeah, they can graph like that basically. So what you do if you want to graphically represent this, you choose a specific value for t, and then you rearrange with that in mind. What is going on out there? Is that why the place was blocked up?
Yeah, probably.
And we can't even close the window, so we just have that big distraction going on out there. So isobaric means like the motion between isotherms. So we have like a complete, what do they call the cycle? You know what it's called? Carnot cycle. So Carnot cycle is we move along an isotherm, and then we switch isotherms, and then we move back up, and then we switch back, right? At one point. Yeah, we move back up, and then we kind of switch back. And that's like an but adiabatic thing. Like they tend to, like in this example here, they split it up to show how much work is done at any point, and that was terribly done. And that goes there. Splits up between this, and it calls it, how do we split up? A here, B, C, D, E. So like how much work has been done at any point in this. So between here and here, you get EAB, gives a movement along an isotherm between these two places. Between here and here, you do D and C. Between here and here, you like minus BC, well, plus BC as a total thing. And then here's just A. Now, as this good a time as any to talk about work. What is work? What is positive and versus and negative work? There's the window. So, positive work is basically if you're doing work on a gas, then we're talking about a negative work. It's how much work the gas does. If you do work on the gas does a negative amount of work. As in, it tends to be like if it's decreasing in volume. Is that the only case? The decrease in volume, or are there other?
Could you repeat that?
When we're talking about work.
Yeah.
Like it's only if you move along the volume.
Yeah.
If you move that way, it's a negative amount of work.
Yeah, I think you're right.
And that is.
Yeah.
There's more. Entropy, which is an equation that I'm pretty sure is not in your data booklet, so memorize it here or from your book. But it's your change in entropy, S, because entropy has an S in it, totes,
Yeah.
equals
Makes sense.
Q divided by T. So when you add energy to your system, I believe it's talking about change in temperature. So when you add energy to your system and it changes to another temperature, that temperature, divide your quantity by the divide your energy by the temperature change, and that's the amount of entropy that you've increased your system by. We talk about the laws of thermodynamics. Let's talk about the 3 laws of thermodynamics. Is it just 3? Is it 3?
Yeah.
Should be.
3?
Like,
Or 2? Isn't there 2?
more dramatic, so I'll make up one.
Yeah, I think too.
Okay. Where's the first law? Really excited about the first law of thermodynamics. Conservation of energy. Energy can be neither created nor destroyed. Q equals delta U. Is it delta U or is it just delta U?
Delta U.
But it gives it as a capital. Plus W. Q and W, so there are 3 U's here, right? According to the English language. So that means that the change in your basically the amount of internal energy that you have is going to be equal to the change in energy plus your work. Basically meaning you can't have something spontaneously get hot. You need to do work to it. You need to work for it. Work for your heat. So that's I think you might have seen Neil deGrasse Tyson with the bowling ball, or I think it was like a bowling ball on a rope. Just held it up to his nose and let it go. Then it came back. Because it's not like going to gain energy unless there's a student hiding behind one of the chairs and popped him really through it. Yeah, if you imagine like a hill here, and you drop a bowling ball down the hill, the maximum height it can possibly reach is that height on the hill, so you don't have to worry about it falling off. Unless you launched it out of a some kind of cannon. And then it went like that, and then it hit that W that was mysteriously floating in the sky and knocked it down. And then everyone went to arrest the person who knocked down the floating letters, which their religion was based on. The second law of thermodynamics. That as time increases, entropy must increase, I believe is the law. Internal process cannot take place for the world behaves. Heat flows. There we go. As time increases, entropy increases, disorder increases. Basically, heat by itself will not flow backwards. If you have a hot thing and a cold thing pressed together, hot thing, cold thing, the heat's gonna flow that way. It's not gonna flow back. That's basically what we talk about when we talk about the heat death of the universe. Saying that eventually all of the heat in the universe is going to spread out as much as possible, and then there will be infinite entropy and we'll all freeze to death because there's not going to be any more heat in any place, and also the universe is going to be so large, or the universe is infinitely large or just very, very big. Either way, there's not enough heat to go around. So yeah, I gave the equation for entropy before I explained what it was, as you do. So any questions, any examples that I should go through?
It's fine for me.
Okay, I'll go through an entropy example, why not?
Yes, entropy.
Hold on. Do you remember that it says the constant temperature to melt the block of ice in this ice? So, let's look at a melting block of ice in a room that is at, so our block of ice, which is blue, in a room that is also blue. melts